Good evening, class. I am Mohit, TA for the Electronic Theory of the Solids course 2025. In today's class, I'll be solving the previous year assignments, which will help you guys to solve the problem which are related on the tight binding model, low dimensional lattices, and the Hall effect, quantum Hall effect. So this is in assignment number 6. I'll start with there will be 10 questions which I will be solving, which are inspired from the class notes, and I'll be solving the problems with which you can get an idea to understand the concepts more better by solving the numericals. And with this one, I'll start. So let me share my screen. I'll share my screen. Share screen. Start broadcast. Yeah. So getting started with the very first question of assignment number 6. This is assignment number 6. So the question says that let us find the k and k prime points in the brilliant zone of the graphene. The Hamiltonian H is given by, so H is about the graphene. So you know that here these terms are actually like energy ground state energy. That E0 that of the single particle atom, but we can shift it to 0. That's why they have been shifted to 0. It's just a constant, so we can shift it to 0. And then this Fk and F star k, they have to do these terms comes when there are carriers which hop from one atom to another. So just that the non-orthogonality of the wave functions, and the electron can hop from one atom to the other, that give rise to the hopping parameters t, and these are the terms corresponding to the nearest neighbor. So Fk is that term. So in order to identify the Dirac points, so Dirac points will be the points in the graphene. These are known as the Dirac points. This point where the dispersion is linear. E is h bar k vf. These points are known as the Dirac points. So at Dirac point, E is equals to h bar k vf. And this is the dispersion. This is the dispersion near the k and k prime points. So k and k prime are the points which are rotated with respect to each other by 180 degree. So its k goes to in the time translation symmetry, k goes to the minus k. So just k goes to minus k prime is equals to minus k under time reversal. Since time reversal symmetry is not broken in this system, so this thing holds. Now it says that okay, find out the coordinates of the k and the k prime point. So if you can find out the coordinates of the k, then k prime will be just the negative of it. So let's start. It says that to find it out, put the fk terms equals to 0. So at k point, fk is equals to 0. This implies e to the power I kxa plus 2i e to the power minus I k x a by 2 cosine root 3 by 2 ky a equals to 0. This gives me e to the power 3 by 2 I k x a is equals to minus 2 cosine 3 by 2 ky a. Similarly, for complex conjugate also equals to 0, f star k equals to 0. So these are the points where energy is 0. So Hamiltonian is basically 0. So the k and k prime are the points where the energy is 0 essentially. That's why we are taking them fk and fk dagger to be 0. Fk conjugate basically. So that will be e to the power minus 3 by 2 I kxa equals to minus 2 cosine root 3 by 2 kya. Let me call this equation 1 and let me call this equation 2. Subtract 1 minus 2. What this will give me e to the power 3 by 2 I kxa minus e to the power minus 3 by 2 I kxa is equals to 0. So we know that the real and imaginary both has to be 0. So it will be cos 3 by 2 I kxa plus 3 plus iota sine 3 by 2 I kxa. This iota won't be there here. So e to the power I kx you can write as cos kx plus iota sine kx. This is how e to the power I kx can be written. So let me write these two here. Kxa minus cosine 3 by 2 kxa and minus iota sine 3 by 2 kxa equals to 0. These two terms cancel each other and this gives the sine 3 by 2 kxa is equals to 0. When this can be possible, whenever this term is integer multiples of n pi. 3 by 2 kxa is integer multiples of n pi, where n belongs to integer. Can be 0, can be non-zero, but it has to be integer. This is the condition number 1. So this is condition number 1. So let me give it equation number 3. So this first condition. Now let's just divide the equation 1 and 2. Divide 1 by 2. That gives me e to the power iota 3 kxa is equals to 1. This tells me that cos 3 kxa plus iota sine 3 kxa is equals to 1. So this has to be 0 and this cos 3 kxa has to be 1. So 3 kxa has to be 1. 3 kxa has to be integer multi 2 n pi, where n belongs to integer. So if you compare the equations, and here also this 3 kxa has to be equals to, but it has to be 0, it has to be equals to n pi. This implies if you combine the equation number 4, 3, 4 and 5, combining 3, 4 and 5 tells me that 3 kxa has to be equals to 2n pi. This will always satisfy the conditions. So this is my equation number 6. So kxa has to be 2n pi by 3a. is my equation number 6. Now let's just substitute this in equation. Substitute equation 6 in maybe equation 1. So if you substitute it, what it will be? It will 3 by 2 I kxa e to the power 3 by 2 I kxa is equals to 2 minus 2 cosine, I think, root 3 by 2 k by a. I think that's the expression, root 3 by 2 k by, right? So if I substitute 6 in 1, so e to the power 3 by 2 I k, instead of kx it will be 2 and pi by 3a, hence a is equals to minus 2 cosine root 3 by 2 k by a. This is nothing but e to the power I and pi to minus 2 cosine by 2 k by a. So it can take value plus minus 1 depending n, if n is equals to 1 or n is equals to 2. This can be equals to e to the power I and pi can be plus minus 1. Right? That tells me that cosine 3 by 2 k by a equals to minus half. Let me solve it for this one first. And if I do it, so it will be root 3 by 2 k by a is equals to 2 4 pi by 3. Then only this condition will be satisfied. 2 pi by 3 basically, not the 4 pi by 3. Pi by 3. This implies the ky to be 4 pi by 3 root 3a. And your kx from the given option is 0. So this tells you that 0 and 4 pi by 3 root 3a for k, and 0 and minus 4 pi by 3 root 3a for k prime. So the correct option is second. This is the first question. Now moving on to the question number 2, which is for graphene the energy spectrum is given by this. For epsilon not equals to 0 and t equal to minus 1, the value of the energy E at point 0.04 pi by root 3 is. Okay. So we have solved it, right? This is the k point. So I can directly say that whatever the energy will be equals to E0, epsilon 0, and epsilon 0 is 0, so that will be 0. But now let's work it out. So E is equals to E naught plus minus T under root 1 plus 4 cosine ky root 3 by 2 a0 cosine kx 3 by 2 a naught plus 4 cos square ky root 3 by 2 a0 at point 0 4 pi 3 root 3a. E is equals to E naught plus minus T under root 1 plus 4 times, if this is the case, it will be minus half plus 4 times 1 by 2 square minus half square. So E is equals to E naught plus minus, this will be T times 0 equal to E naught. For E naught is equals to 0, this implies E is equals to 0. So The correct answer here will be 0. That's the answer for this. Now, moving on to question number 3. For a two-dimensional unit square lattice, what value of E corresponds to half-filled band? Take epsilon naught equals to 4 and T is equals to 1. So, moving on to question number 3, that for a two-dimensional unit square lattice, for a 2D unit square lattice, what value of E corresponds to half-filled band? Okay, so we know that the energy for the 2D unit square lattice from the class notes is E is equals to E0 plus minus, no need of plus minus, I can put it like 2T cosine of kxa plus cosine of k by a. If it is confined in z direction and can move in the x and the y direction, then this is the expression of the energy. Now, for epsilon 0 is equals to 4 and e is equals to 1. E is equals to 4 plus 2 cosine of kxa plus cosine of k by a. This function can take maximum value of 2 and minimum value of -2. Whenever maximum will be possible when kx a equals to ky a equals to 2 times capital N pi, and minimum will only be possible when kx a equals to ky a equals to 2n plus 1 pi, right? In that case, maximum energy Emax will be 4 plus 2 times 2, that will be 8. Minimum energy E minima is equals to 4 minus 2 plus 2 is equals to 0. So it is like E max, E minimum is E minimum is equals to 0, E max equals to 8. At half filled, the point at which the energy is half filled will be what? 8 plus 0, 8 minus 0 by 2, that will be 4. So the correct answer here is 4. Now moving on to the next problem, that for a square lattice at very low filling, the shape of the Fermi surface is square, a distorted square, a circle, or a distorted circle. Okay, let's figure it out. So first we have to write the energy expression. Energy expression will be E is equals to E0, that we have written in the previous problem also, minus 2t cosine of kxa plus cosine of kya. Right? Now, for low filling, since k directly proportions to root n, k will also be very small. Such that kxa is also small. Therefore, Therefore, the term Kxa and Kya will also be small. So if this is my equation number 1, what I can do, I can write it as like E is equals to E naught minus 2t. Cosine I can expand. 1, so let me first write the cosine expansion. Cos x expansion goes as 1 minus x square upon 2 factorial plus x to the power 4 upon 4 factorial minus x to the power 6 upon 6 factorial and so on. For small x, I can write it as cos x is equal to 1 minus x square upon 2 factorial. And the rest of the term I can neglect. Right? So if you substitute this, substituting 2 in 1, what will you get? E is equals to epsilon naught minus 2t. Cos kx you can write 1 minus x kx a square upon 2 factorial. Rest term you can neglect plus 1 minus ky a square upon 2 factorial. Rest higher order term you neglect. Now you can write it as e is equals to e0 minus 2t. 1 plus 1 will be 2 and minus kx a square by 2 ky a square by 2. E is equals to e0 minus 4t plus kx a square plus ky a square. Right? So now you can, e naught is constant, 4t is also a constant because hopping parameter is a constant. So what you can do, you can write it as like a kx square plus ky square is equals to e minus e0 plus 4t by a square. So if let me write it in some different form, x square plus y square is equals to c square. This is an equation of circle. If you compare these two, so this is my equation number 3, this is my equation. So isn't 3 and the equation number 4 comparing 3 and 4 tells me that at low energy dispersion will be circular. High energy it is a distorted circle, but at low energy it will be a circle. Okay. If you have any doubt or questions, suggestions, you can always write in the comment box. I'll be happy to address your concerns. Okay, no question. I will move on to the problem number 5. Which of the following statement is false? In lower dimension, a chain of one atom per unit cell gets distorted to form two atoms unit cell. So what is saying that which of the following statement is false? But let's understand the first problem. First statement. The first statement says that there is a chain of 1D atoms. Okay, fine. Let it be. In lower dimension, a chain of one atoms per unit cell gets distorted to form two atoms unit cell. Okay, what happens under strong electron phonon under strong phonon coupling? What happens? This atom will move like this. This atom will also move like this. This will move like this. So instead of this will be here. So if the initially the lattice length was A, now it will be 2A because it is more energetically favorable. So yes, it can happen in the one dimensions. Electron phonon coupling is responsible for the Bohr distortion. Yes, It happens because of electron phonon coupling. This is absolutely right. The final energy depends on whether the atoms moves right or left. Let's see. Let's draw the figure, and then you only will be able to tell me that okay whether it will depend or not. So if my lattice was like this, initially my lattice was like this, for example, and it is extending to infinity after moving to right. To right. So let's move this one to right, this one also to right, this one also to right. Let's see what happens. So it will be like this. So this atom moves here, and there will be space that moves here, and, right. So initially it was A. Initially it was A. Now it is 2A. Let's do after moving to left. So if in case if they move to left, what will happen? Here, then there will be nothing. Here, and here. This is also true. But I can, oh, okay, let me just then copy it after moving to right. Let me just copy this thing and let me put it here. I can translate it, right? Because it's an infinite lattice, I can just translate it like this. See, they exactly lie on top of each other. It means they are like identical, whether it moves left or right. So if they're identical, the translation symmetry is not broken, nothing is changed. So the final energy will not depend on whether the atoms move right or left. It depends whether the atoms move or not, but don't depend on the direction. So this statement is also true. Now the statement, this statement is false actually. This statement is false because this tells that the energy depends, but the energy will not depend. Now the problem number 4 is it is extremely difficult to form a regular crystalline lattice in one dimension. No. The 1D lattice do exist, and it is not extremely difficult. It can be difficult, but not extremely difficult because they do exist. So, so this the correct answer here is third, which is false. Now, moving on to the problem number 6, which of the following is true for a low-dimensional system? Electronic structure of nanostructure is independent of size. See, it depends. Electronic structure. Electronic structure depends on the lattice spacing. That we know, right? Because K is pi and pi by A. We know that at those points the gap will open up. We will study electromechanical model. If one can alter the A lattice constant, the band dispersion can be altered. So the electronic structure depends on the nanostructure size. Of course, it depends. And dimensions also depends whether it's a 3D, it's 2D, it's 1D, because we have seen if it's 3D, its density state will go as e to the power half, but if it is density state will go as e to the power 3 by 2. If it's 2D, its density state will go as uh, constant e, but if it is 1D, its density state will go as e to the power minus half. I think that's what it is. For 1D, for 3D, it goes as e to the power half. For 2D, so that's constant. For 1D, it is e to the power minus half. I think that's what it is. So if I draw the shapes, it will be like this. This is POS, this is POS, it will be constant. And in this case, POS, it will be like this. Following. So the first option is false because the electron structure depends on the size. The surface to volume ratio decreases as we decrease the size. Okay, let's do write it. So let's assume assume to be sphere. Surface area is 4 pi r square. Volume is 4 by 3 pi r cube. Now it's saying surface to volume ratio. Surface to volume ratio is proportional to 1 by r. As one decreases r, surface to volume will increase. But whatever given in the option is false. The surface to volume ratio decreases as we decrease the size. No, it increases. So this is false. This is also false. The energy spectrum becomes discrete rather than continuous. Let's see. So if your atoms are closely spaced, your atom spacing is A, for example, if it is A, your energy will be h bar square k square by 2n, and k can take value n pi by A, right? So this is what n pi by L, if L is your length of the system, like basically. So it's depending. If L is very large, your E versus K will be like continuous. But if L is small, K can take only K can. E versus K will be discrete. It is always discrete, but if L is very large, then you can treat it like a continuous. But if L is very small, you have to treat it like discrete. What does that mean? I mean like this. This is your E versus K. For continuous system, they will be like so closely spaced that you can treat them like if they are continuous systems. For large L, but for smaller L, they will be like one here, one here, one here, one here, one here, one here. So discreteness increases. As L decreases, discreteness increases. It becomes more visible. That's what it means. The energy spectrum becomes discrete rather than continuous. Yes, this is true. Now, option number 4, Schrodinger equation is no longer valid at extremely small scale. No, it is valid. It is valid because it's a quantum mechanical. It is a quantum mechanical equation. It is valid like in all the regimes. So Schrodinger equation is always valid. So this is false. It's not. There's when this is no longer valid. It's false. It's always valid. So if you have any question or doubt, you can ask me. Else I will move on to the next problem, which is problem number 7, which says that consider a doped semiconductor in which each donor atom gives one electron each to the impurity level. If the whole coefficient at room temperature is RH is equals to 6.25 into 10 power minus 6 meter cube coulomb inverse, then the number of donors is n times 10 to the power 24 meter cube. The value of n is, okay, what they are asking is the carrier concentration, right? So let's just do it. We know that the whole coefficient RH is nothing but 1 by ME. So there is a doped semiconductor in which each donor atom is 1 electron, the impurity level. So each number of 3 electron equals to number of donors times electron given by each donor. In this case, this quantity is 1. So number of electron equals to number of donors. Right? Now RH is given. RH is equals to 6.25 into 10 power minus 6 meter cube Coulomb inverse. The number of donors is, okay, if this is this, then N will be 1 by RHE. This implies 1 by 6.25 into 10 power minus 6, 1.6 into 10 power minus 19. This gives to be 6.25 into 1.6 will be 10. So 10 will 10 power minus 5, the 10 power 24, 1 into 10 power 24. So here the question is n times 10 power 24 meter cube. This implies n is equals to n in the problem. So n of the question is So here the correct answer is 1. Now moving on to the problem number 8. The low energy electronic excitations in a two-dimensional sheet of graphene is given by h bar kVf, where Vf is the Fermi velocity. The density of state is proportional to. So Ek is given. It is h bar kVf for 2D systems, for two-dimensional system. Number of states equals to n is equals to 2 is the spin degeneration and spin degeneration. 2 is the valley degeneration, that is the kk prime of graphene times 0 to k area a times, so let me write it like d2k upon 2 pi pi l lx ly 2 pi by lx and 2 pi by ly. So I can write it like n is equals to 4 times d2k is nothing but pi k square by 4 pi square times area, and by a is equals to density of step number their density is equals to pi k, k square by pi is equals to k is proportional to under root K is equals to under root n pi, right? So this will be my equation number. This is my equation number 1, which is given in the question. This is my equation number 2. So if I take E density of state, density of state, density of states is what? Number of states per unit energy, del N by del E. Right? That's the density of state mean. So if I take EK, instead of write EK, let En is equals to H bar instead of K, right? Under root N by Vf, and del E by del K. Del E by del N is nothing but H bar Vf. Let me just do it slightly the other way. E square equals to H bar square Vf square, and pi and del N by del E will be equals to 2 E by H bar square Vf square pi. So density of state is proportional to E energy. So the correct answer, the correct option here is 1. Density of state here is proportional to E. This is problem number 8 solved. Now moving on to the problem number 9. Which is a Hall effect probe is placed on an artery. One artery is there which carries the blood. Applying a 0.1 Tesla magnetic field across it. In a setup similar to that in the figure below, what is the whole EMF given the vessel inside diameter is 4 mm and the average blood velocity is 20 centimeter per second. Okay, magnetic field is given B, that is 0.1 Tesla. So setup is given, so the blood flows in it, this is the artery, and magnets are placed here on the two ends. This is north and this is south. Now if this is the case, velocity is like this, the force will be on the upsides, and there will be an EMF across these 2 points, which will be EMF. Right? Now B is 0.1 Tesla. You know, in a setup similar to that in the figure below, what is the whole EMF? So Rxy, we write it as B by NP, right? We write it as B by NP, and B is equals to what? I times R. So V and EV is equals to EMF. Is I R X Y times E. Right. So if I write it, it will be EMF is equals to B by N times I. So what is the carrier density here? So I can write this n by I time equals to b times this n. I can write like 1 by whatever the number of carriers are there, or carriers per unit volume, right? So n by volume is how much? Is 4 mm is the diameter. 4 mm in, given the vessel inside diameter. Diameter is given 4 mm. So it will be pi r square. So it can be written as by pi d square by 4. Right? And then the length will be 20 centimeter per second. 20 into 10 power minus 4 per second. Current is nothing but charge going 28 area, right? So that will be the, so this is p I by n can be written as simply b times pi d square by 4 times 20 into 10 power minus 4 by no. Sorry. Here's a mistake I did. So EMF here it will be nothing but b times d times whatever the speed is there, blood velocity. It will boil down to that equation, and 0.1 Tesla times d is 4 mm, 4 into 10 power minus 3 into blood velocity is 20 into 10 power minus 2. So if you solve it, it will be 2 8 to 10 power minus 5 or 80 microvolt. That will be the EMF. So the correct option here is 80 microvolt. Now moving on to the last problem, which is considered a similar setup as that of the Hall effect discussed in the lecture. If the spin degree of freedom of electrons are also considered, which of the following would be correct? You know, in the Hall effect, this is my Hall effect. This is my source. This is my drain. So the carriers will drift along these 2 points AB. RAB is VAB is Hall voltage. Hall voltage. Now, if now if spin degree is also considered, then under strong spin orbit coupling, that is k dot sigma is equals to constant is coupled, k is momentum, is spin, momentum spin locking. Okay. Then spin up will go in one direction because so for up spin sigma is equals to, for example, let's say plus half. For down spin sigma equals to minus half. This implies k half plus half will be minus k minus half. So if the up spins are moving like this, they will drift on this side, and the down spins will drift on the other sides. This on one end, on A end there will be an up spin, then on the B end there will be down spin. So that's the up and down spin of the electron gets accumulated on the opposite surface of the sample. Yes, this is true. Analogous to the current generated by the charge, spin current is observed in the experiment. Yeah, if one can measure the spin current, yes, there will be a spin current between the A and B. And how it is done? It is measured by Landau-Buttiger method. Buttiger method. If there are edge states, if there are non-zero churn number, then it can be measured using the Landau-Buttiger. The up and down spin gets accumulated in the surface of the sample following the Pauli exclusion principle. No, this is not true. Here the momentum value locking is there, spin momentum locking is there because that they are drifting in the opposite direction, not because of the Pauli exclusion principle. So 1 and 2 are true. So first and second are true. So this is the correct option. Correct option. The rest all are false. So here the other two. This is the assignment number 6. I will go over it once again. So what we solved in this class. So starting from the first question, what we did is, so the question says that this is the dispersion relation. This is the Hamiltonian of the graphene. What is the this is the Hamiltonian of the graphene, and the question asks what is the kx and the ky value at the k and k prime point. That is the point at which the energy of the dispersion relation is 0. And for that, we take the fk equals to 0 and fk conjugated to be 0, and that gives the correct answer to the second 0 plus minus 4 pi by 3 root 3. And that's the correct answer. Now moving into the second question. For a graphene, the energy spectrum is given by E is equals to E0 plus minus T under root of this quantity. And they ask that what is the value of the energy E at the point 0, 4 pi by 3 root 3. We know that this is the k point coordinate. We calculated in the previous question, but we still do it. And what we find that this term goes to 0, and the energy is equals to E0, and E0 since here is 0, so the total energy E is equals to 0. That's the answer for this question. Now moving on to the problem number 3. For a 2D unit square lattice, what value of E corresponds to half filled band? We write the energy dispersion relation is equals to E0 plus 2T cos kxa plus cos kya. Now for E0 is equals to 4, T equal to 1, but we find that E is equals to 8, E max is equals to 8, E minimum is equals to 0, and at half filled this will be the average of 2, that will be 8 minus 0 by 2, that will be the 4. The correct answer here is, this problem is 4. Now moving on to the next question. For a square lattice at a very low filling, the shape of the Fermi surface is, so we take the energy relation to be up to the first coping term, E is equal to 0 minus 2T cos kxa plus cos kya. And then for smaller k, we write cos x equal to 1 minus x square by 2 factorial, neglect the higher order terms. We substitute it in equation number 1 for low fillings, and what we get is the equation of the circle at low energies. That tells me that Comparing equation 3 and 4 tells me that the flow energy dispersion will be circular. Now, to problem number 5, which of the following statement is false? In lower dimension, a chain of one atom unit cell gets distorted to form two atoms unit cell. Yes, it can happen if the system is minimizing its energy by doing so, and it requires strong electron phonon coupling. Then the second question is electron phonon coupling is responsible for above distortion. Yes, this is true. The final energy depends on whether the atoms move right or left. No, this does not depend. We showed it here also. That since it's an infinite lattice, it only depends between the what is the separation between the lattice, that is the two-way for both left or right movement. It does not change the Hamiltonian. What is and then the next option, it is extremely difficult to form a regular crystalline lattice in 1D. No, it can be done. It can be done with both with the optical tweezers, and in the normal system also it can be done with the crystalline lattice 1D wires, like kind of things. Which of the following is true for low dimensional system? Electronic structure of nanostructure is independent of size. No, it do depend on the size. Then the surface to volume ratio decreases as we decrease the size. We showed that no, this is not the case. The surface, as one decreases R, surface to volume actually increases. It's reverse of that. This is also false. The energy spectrum becomes discrete rather than continuous. Okay, we showed that the K is n pi by L, and as one decreases the L, the dispersion becomes more of discrete. Here it was more of continuous side. So yes, this is true. The correct answer is 3. And the fourth one is Schrodinger equation is no longer valid at extremely small scale. No, it is actually valid at extremely small scales because it's a quantum mechanical equation. Now, the problem number 7 is consider a doped semiconductor in which each donor atoms gives one electron each to the impurity level. If the whole coefficient at room temperature is given, then the number of donors is the value of n is. The whole coefficient is given, Rs is equals to 1 by Ne. Number of free electron equal to number of donors times electron given by each donor. So number of free electron equals to number of donors. Rs is 6.25 10 power minus 6 meter cube coulomb inverse. Now n will be Rs by E. So we calculate it, and the value of n comes to be 1 in 10 power 24. The question asks the front term, which is 1. The prefactor of 10 power 24 is that is the 1. That is the correct answer. Then for the graphene, E equals to H bar kbf dispersion is given. We then we start looking for relation between n and the k, because density of state is del n by del E. So we have to convert n into k, or k into n first. We do it. K is equals to under root n pi, and E density of state is equals directly proportional to energy. So here the energy should be there. Yeah, directly proportional to energy. Now in the next question, there is an artery which is clamped between the two magnets, and then they ask why the EMF induced. EMF induced will be B times D times the blood velocity, and that gives the 80 microvolt. Now moving on to the last problem. Consider similar set as that of the quantum Hall effect discussed in the lecture. Spin degree they are allowing. So if you allow the spin momentum to be locking, the upward and the downward spin will move in the opposite direction that we have seen. That's true. Analogous to the current generated by charge, spin current is observed in the experiment. Yes, this is true. If there is a non-zero charge number, then one can observe it by the Landau-Boettger experiment. And the up and down spin gets accumulated on the surface of the sample following the Pauli exclusion principle. No, it's not because of the Pauli exclusion principle. It has to do more with the spin momentum locking. So with this, I will end the class. If you have any question, doubt, or suggestion, you can always write it in the comment box of this Teams channel, or whether in the YouTube video comment section. I'll be happy to address your questions.